Hello everybody, and welcome back to another episode of Maths. Hope you're all having a great day today, and it's about that time again. It's checkpoint time.
Oh, yeah.
So, if you're not familiar with the checkpoints, basically these are ways for us to test everything we've kind of covered in this last unit. And this unit is going to be everything from episodes 35 to 47 in the Fundamentals of Algebra series. I have recorded a couple of other ones that I've posted already, kind of on order of operations, but I've decided to make that its own separate unit, so that's not going to be included in today's video. It's just going to go up to episode 47, where we talked about kind of additive and multiplicative inverses. Because this checkpoint is a test, I would recommend before you take this test to go back and look at kind of all the things that were covered in this unit and make sure that you're kind of comfortable with all those concepts. Maybe you need to go back and rewatch some videos or some parts of some videos, or try out some of the practice problems to kind of get more of a swing for things, but I strongly recommend kind of reviewing the things in this unit first and then trying out the checkpoint for yourself. Try the questions yourself first before we go into them together. So I'm going to flash all of the questions on the screen now. Again, pause the video, try them out yourself first, and then let's go through them together. Question 1. All right, so let's start with the first question. So it says, I know 702 over 5 is 140.4. Explain how I can use this to convert 702 over 50 into a decimal. So this was from one of our mental math videos, and right off the bat, I can know that this is 14.04. So that should be the answer, but how did I get that? If you're not sure, you should go watch the video. This was Fundamentals of Algebra 35.5. However, the way I did this is essentially, since the only difference between this and this is that this 5 is now a 50 in the denominator, essentially that means is I've added a factor of 10 in the denominator, or I've essentially kind of divided this 702 by a 10, which means I've divided the overall result by a 10, which means I've slid the decimal to the left by 1. So that's how I knew to get 14.04. But again, if you're not sure about that trick, I explain it in much more detail in episode 35.5. Question 2. All right, question 2, we've got a few expressions we need to evaluate involving fraction stuff. So the first one, we have 3/5 times 1 and 6 over 7. So this mixed number is kind of throwing us off a bit, so it might be a good idea for us to convert this mixed number into a improper fraction, because we know fraction multiplication is just multiplying the numerators and the denominators. So in order to get that, let's convert this into an improper fraction first. So the way we can convert this into an improper fraction, this is review from the previous unit. This is going to be 7 times 1 plus 6, which is 13 over 7. If you need review on converting mixed numbers into improper fractions and vice versa, please check out episode 29 of this series. That's from the last unit. So now we have 1 6/7 expressed as an improper fraction. We can take this product here and re-express it as 3/5 times 13 over 7. And now we can just multiply the numerators and the denominators. 3 times 13 is 39. 5 times 7 is 35. And this will be simplified here. And if you want review on how to multiply fractions, that was episode 35 of the series. All right, so for part B, we have 4 over 7 divided by negative 21 over 8. And dividing by a fraction is the same as multiplying by its reciprocal. So we end up getting 4/7 times 8 over negative 21, right? We've just taken the reciprocal of that and converted the division into multiplication. So now all we have to do is just multiply the numerators. 4 times 8 is 32. And multiply the denominators. 7 times negative 21, you will find, is negative 147. And for part C, we have 5 over 3/5. So this is actually another fraction division problem, because we know an overall fraction is division. So this is really the same thing as 5 divided by 3/5, which is the same thing as 5 times the reciprocal, which is 5/3, and this becomes 25 over 3. So for parts B and C, those were covered in episode 46 of the series. Question 3. Okay, so for question 3, we've got these three numbers. We have 3/5, 2/3, 6, and -4/5. And part A asks us to find the additive inverse of each of the above numbers. So the additive inverse is basically the opposite of this number, but where we're thinking of it as a shift or in the additive sense. So 3/5 thought of as a shift is basically we've gone from 0 to 3/5 to the right of it. So the opposite of that would be going 3/5 to the left, or shifting to the left 3/5. So the additive inverse then would be -3/5. Similarly for 2/3, we're just applying the negative to get the additive inverse, so we get -2/3. Similarly for 6, we get -6, right? It's all the same thing. Normally we're moving to the right by this amount, but now to move to the left by this amount, we're just applying that negative. However, for this -4/5, we're starting off to the left of 0, so to do the opposite of that in the additive sense, we need to go to the right of 0 that amount, so the opposite would be +4/5. All right, so that is part A. And if you weren't sure about that concept, please go check out episode 47 of this series. For part B, it asks us to find the multiplicative inverses now, not the additive inverse. So the multiplicative inverse is basically how we can think of the opposite of this number in the multiplicative sense or in the stretching sense. So what's the opposite of 3/5? Well, that's going to be to take the reciprocal of it, because the opposite of 3/5 when it comes to multiplication is basically we're undoing the numerator, which is a stretch by 3, so that puts the 3 in the denominator, and we're undoing the denominator, which is a compression by 5, so that puts the 5 in the numerator because it's a stretch now. So this equates to us taking the reciprocal of this. So then with the same logic, the multiplicative inverse or the reciprocal of 2/3 is 3/2. And for 6, well, 6 is the same thing as 6/1. So the multiplicative inverse of that, or the reciprocal of that, would be 1/6. And for -4/5, the reciprocal of that would be 5/4. Okay, so that is the multiplicative inverses of those. And like with part A, you can watch episode 47 of this series, and you will find part B easier to handle. Part C asks us to find the average of the above numbers. So to find the average, that requires us to add up all the numbers and divide by the amount we have. So that's going to essentially mean we have to do 3/5 plus 2/3 plus 6 plus -4/5, and then divide all of that by 4 because we have 4 numbers, right? So let's start with the sum on top, and it'll probably be easiest if we make a common denominator, which in this case should be 15. So now that we know 15 is our common denominator, we're going to have to multiply this 3/5 numerator and denominator by 3 each, because that'll make our denominator 15. 2/3, we're going to have to multiply the numerator and denominator by 5 each. 6, that's the same thing as 6/1. So we're going to have to multiply the numerator and denominator by 15 each. And then -4/5, well, to get the same common denominator, we're going to need to multiply the numerator and denominator by 3 each. So let's see what that gives us. We get 9/15 plus 10/15 plus 6 times 15 should be 90/15. And then adding a negative is the same as subtraction, so we can replace that with a minus sign. And then this will become 12/15. And all of that over 4. So adding up and subtracting these numerators here, we get 19 plus 90 is 109, minus 12 is going to be 97. And then 97/15, all of that divided by 4, that is going to be the same thing as, we can actually just combine these denominators here because it's the same thing as 97/15 times a quarter, or we could take the reciprocal, but ultimately we're going to get 97/15 times 4, which is going to be 97/60. And this is going to be our simplified answer. So if you need some review on how to find the average of some numbers, please go and check out episode 45 of the series. All right, and part D of question 3 says, which of the above numbers can represent the proportion of high schoolers in a room of 6 people? Okay, so we have 6 people in a room, right? So we've got 6 people right here. And a proportion of them means basically some piece of them is going to be high schoolers. So, for example, one possibility is that we have 5 of those people being high schoolers, so that in that case, the proportion would be 5/6, right? But this is saying out of these numbers up here, which one could be the high schoolers? So we can rule out -4/5 because you can't have a negative proportion. We can also rule out the 6 because it doesn't really make sense for us to have a proportion that's bigger than 1. The maximum amount of people here would be 6 high schoolers, but that would give us 6 out of 6, or a proportion of 1. So we're not going to be exceeding 1, so 6 isn't possible. So we're looking at either 3/5 or 2/3 as our last two possibilities here. But the thing is when we get a proportion here, it's going to be a proportion out of 6, right? We could have 5/6, or maybe 1 of the 6, or 2 of the 6, right? So these are all possibilities. But neither of these have a denominator of a 6. However, this one has a denominator of a 3. And a denominator of a 3 is possible because if we look at, for example, 2/6, that simplifies into a third, right? Since 3 is a factor of 6, it's possible that our proportion will simplify into something with something over 3. However, if we have a denominator of 6, our proportion is never going to simplify into something with a denominator of 5. So what this means then is that 2/3 will be feasible. And in fact, that will happen if 4 high schoolers are in this group. So then that would mean that 4 of the 6 people are high schoolers, and that simplifies into the 2/3 that we're looking for. So 2/3 is the only possible number of these that can actually represent a proportion of high schoolers from this group. And that would be specifically when we have 4 high schoolers. Question 4. Hey there, Vape Memes 2020.
How are y'all doing?
Oh, I'm doing all right. What are you doing with that blunt object?
You know, you
No,
know.
no, don't.
Question 4.
Okay, so question 4 says, suppose 2/3 of my symphony are aerophones and 1/5 are chordophones. And if you don't remember what those are, that came from the Hornbostel-Sachs instrument classification system, which we went over in depth in episode 36 of the series. So I encourage you to go watch that. That's also going to be helpful for a few of these parts of this question. So if you're not familiar with that, please go watch that video now. So 2/3 are aerophones, basically instruments that make sound by vibrating air. And 1/5 are chordophones, so that's instruments that make sound by, plucking a string or vibrating a string in some way. So part A says, if there are 60 people in the symphony, what's the maximum amount of trumpets I could have? Okay, so trumpets are aerophones, right? They make sound by vibrating columns of air. And since 2/3 of the symphony are aerophones, now that doesn't mean all of them are trumpets, right? But that means the trumpets are going to be included in this proportion, right? So the maximum amount of trumpets is essentially saying that if all of this proportion, all of this 2/3 were trumpets, that would be like the maximum amount of trumpets we could have. So all we have to do is basically apply this proportion of 2/3 to the 60, and that will tell us basically how many instruments in our symphony are aerophones, and then that's going to be our maximum amount of trumpets. So if we take our 2/3 and we multiply it by 60, right, that's applying our proportion to the 60, then what this is going to be is we will get 120/3, and that simplifies to 40. So that means 40 of our instruments are aerophones. So that means that since trumpets are included in those aerophones, the most amount of trumpets we could have is if all of these aerophones are trumpets, we don't have any trombones or anything else, it's just pure trumpets, then that would mean that 40 is our maximum. So if you're not sure about that problem, again, that came from episode 36 of this series. All right, part B says, what percent of the orchestra are chordophones? Okay, so we know that the proportion is 1/5, but it's asking for the percent. So all we have to do is convert this 1/5 into a percent, and that will tell us what percent of the orchestra is chordophones. So to convert 1/5 into a percent, one way we can do that is by making this into a fraction out of 100, which isn't too bad because 5 is a factor of 100, And if we do 5 times 20, we're going to get to 100. So this becomes 20 over 100. And since a percent is per 100, that means this is the same thing as 20%. So 20% of the orchestra is made up of chordophones. And if you want some review on how to convert between proportions and percentages, or between percentages and fractions, and so on and so forth, please go check out episode 39 of the series. Part C says, I randomly choose one symphony member to steal their instrument. How devious. What's the probability I get an aerophone or a chordophone? So in order to figure out the probability of getting an aerophone or a chordophone, we need to know the probability of getting each one individually. But that's not bad, because the proportion is actually the same as with the probability of basically choosing one at random and getting something that is in that group that the proportion represents. So if I wanted to look at the probability of getting an aerophone, that would be the same as the proportion of 2/3 or a probability of 2/3. These were just kind of two perspectives on the same thing. So the probability of getting an aerophone would be 2 in 3. And the probability of getting a chordophone is going to be 1 in 5. But it wants us to figure out the probability of getting one or the other. So in order to combine these probabilities, when we look for one or the other, we need to add them. If we were to multiply them, that would be the probability of getting one and the other. But in this case, we need to add these two because we are looking for the probability of one event or the other. So we do 2/3 plus 1/5. So we need a common denominator, which is going to be 15. So multiplying this one by 5 each to get 15, and multiplying this one by 3 each to get 15, we end up getting 10 over 15 plus 3 over 15, which becomes 13 out of 15. So there's a 13 in 15 chance that we either get an aerophone or a chordophone. So fairly likely. And if you need some review on kind of these combining probabilities, please check out episode 42 of the series. All right, so part D says, what's the maximum amount of drums that could be in the symphony? Drums are neither aerophones nor chordophones. Drums would be an example of membranophones. So they aren't aerophones or chordophones. So because drums are neither of these, that means that they are not going to be included in the proportion of the symphony that are aerophones or chordophones. But we know the proportion of the symphony that are aerophones and chordophones. That's the 13/15, right? So 13 out of the 15 is either an aerophone or a chordophone. So that means the drums, being neither of these, is going to have to occupy the remaining amount of this. Or we also call this the complement of the 13/15. So the drums are going to be a part of the remaining proportion. But what's remaining? Well, that's going to be 1 minus 13 over 15, which is 2/15. So there's 2/15 remaining, which means that if we're looking for the maximum amount of drums, that means that that will occupy the entirety of that proportion. All the drums are in this 2/15 of the total. That means that the maximum amount of drums would mean that this 2/15 is entirely comprised of drums, no other instruments. So to figure out the amount, so we just apply the 2/15 to the total instruments, which are 60. So 2/15 times 60, that's going to be 2 over 15 times 60 over 1, which is 120 over 15. And that should simplify down to 8. So there's a maximum of 8 drums in this symphony. And for part D, once again, the video you'll find most helpful with that will be episode 36.
Question 5.
Question 5 says, I run a test to see if the relative frequency of gunpowder dropped by creepers in Minecraft is close to the probability. So creepers, they are a type of enemy in the Minecraft game, and when they die, they drop gunpowder. So for part A, it says, what would you recommend I do to test to make sure the relative frequency is as close to the true probability as possible? So in episode 43 of the series, we built kind of a contraption that allowed us to test the relative frequency of mob drops. And the relative frequency, to review what that is essentially just the amount that we've observed of the event that we're testing. So in this case would be basically the amount of times we see like one drop or two drops or three drops. And then we are taking that amount and dividing it by the amount of trials that we did. So it's basically the relative frequency is the number of event observed divided by the number of trials. We want to see if the relative frequency of creepers that dropped one gunpowder, if that's close to the true probability, and the relative frequency of creepers that dropped two gunpowder is close to the true probability, and so on and so forth. So that was kind of the point of the test. And so part A says, what would you recommend I do with this test to make sure the relative frequency is as close to the true probability as possible? Well, we have a relationship between the relative frequency and the true probability, and that's the more trials you do, eventually the relative frequency for a large enough number is going to be close to the true probability, and if we do this infinitely, it becomes the true probability. And this was called the law of large numbers. So what this means then is that we want to do more tests. If we do more tests, it'll help ensure that the relative frequency gets closer to the true probability. By the law of large numbers, that's our justification for this. We want to do as many tests as possible to ensure that the relative frequency gets as close as possible to the true probability, because the bigger the amount of trials we do, the closer that relative frequency on average is going to get to our true probability. And again, if we did this infinitely, which of course we can't, but we can do a lot, right? We could do thousands or maybe even millions of trials if we have a lot of time or a lot of computing power. And that's going to help ensure that our relative frequency is quite accurate to what the true probability is. So for that one, kind of this law of large numbers, that's discussed in depth in episode 41 of the series. So part B then says, I do 2 tests with 1,000 trials. One to test gunpowder drops when killed without looting, the other to test gunpowder drops when killed with looting 3. Which test should we expect to have the more accurate relative frequency, and why? Okay, so regularly, creepers only drop 1 gunpowder. However, when you kill them with looting 3, that increases the chances of additional drop. We saw this when we discussed this in episode 43 when we were doing this with zombies. But essentially, without looting, we only have a certain amount of possibilities, right? Maybe either 0, 1, or 2 gunpowder, or maybe 0, 1. Maybe you don't know the exact amount they drop, but there's only a few possibilities without looting. But with looting, because that adds extra drops, we suddenly get more possibilities, right? And so what this means then is that if I do 1,000 trials for both of these, we're going to get relative frequencies for both of for each of the events, right? So there's going to be a relative frequency for no gunpowder, a relative frequency for 1 gunpowder, and so on and so forth. But for when we do the trials with looting, we're going to expect that the relative frequency is actually a little bit less accurate. It's a little bit rougher because we're essentially spreading the 1,000 trials over more things, right? And since we're spreading them out over more things, it's going to be less accurate. Okay, so without looting, we'll be expected to have a more accurate relative frequency as there are less outcomes represented by the same amount of trials, right? Both 1,000 trials, but only 3 outcomes versus maybe 5, meaning that more trials can be allocated to these outcomes. Like, once again, we discussed all of this in episode 43.
Question 6.
Question 6 here goes through a bunch of the perspectives that we have on fractions, and we talked about a lot of perspectives in this unit. So the first part says, what does 2/15 mean as a proportion? So 2/15 as a proportion basically means that this represents kind of the piece of a group that has maybe a certain property. So we would say then that basically 2/15 of the group has a property. So maybe the group is 15 people, in which case 2 of the people have that property. But it's also possible that the group has more individuals in it than 15, but the piece just simplifies down into 2/15. But whatever the situation is, this kind of represents the size of the piece of the group that has a certain property. So what we end up getting is that It represents the size of a piece of the group with a certain property. So we take the number with the property and we're doing it over the size of the group, and that simplifies down into 2/15. So that perspective was discussed in depth in episode 36 of the series. For part B, it says, what does 2/15 mean as a probability? So a probability is basically how many times we expect something to happen out of a certain amount of trials. So 2/15 as a probability means we would expect something to occur twice out of 15 trials. So this kind of represents the likelihood of something happening. And one way to think about that is how frequently it occurs out of a total amount of things. So how frequently it occurs relative to all the other possibilities in a sense. And we discussed this probability perspective in depth in episode 41 of the series. All right, next up it asks, what does 2/15 mean as a double action? So we talked about the double action perspective as essentially when we thought about 2/15 as being maybe 1 times 2/15, where we can think about the number itself as an action, then we saw that the numerator is a stretching, and so we get that this is a stretch by 2, but the denominator being over 15 or dividing by 15, that corresponded to a compression. So 2/15 represents a stretch by 2 and a compression by 15. And we discussed this perspective in depth in episode 37 of the series. And lastly, it asks us to convert 2/15 into a percent. So because 15 isn't a factor of 100, the best way to do this is just going to be, let's do 2 divided by 15 and do some long division, get a decimal, and we'll convert that decimal into a percent. All right, so doing long division, we get 2/15 is 0.133, and the 3 just keeps on repeating. So when we convert this into a percent, well, all we have to do is we have to multiply by 100%, because that's the same as multiplying by 1. And that is going to be equivalent to us sliding this decimal to the right by 2. So we're going to get 13.3 repeating percent as our result. So another perspective we can take on 2/15 is as the standardized proportion, which is 13.3 repeating percent. And we talked about how to do these conversions in episode 39 of the series.
Question 7.
Okay, question 7 is a true or false, and we've got 3 parts to it. So first one says, every average is an example of a weighted average. Okay, so an average is where we take a bunch of numbers and we divide them by the amount we have, whereas a weighted average is where we take all of the numbers and we multiply them by some weight, and it has to add up to 1, these weights. Well, it is going to be true, because for example, if I did something like the average of 3 numbers, we know this is the same as I'm able to basically split this up into doing 1/3 plus 2/3 plus 3/3, which is the same thing as doing 1/3 times 1 plus 1/3 times 2 plus 1/3 times 3, right? I'm essentially taking all the numerators and I'm multiplying them by 1 over the denominator. But when we take these 3 denominators, a third plus a third plus a third, and we add them up, we end up getting 1. Right, so we do see that this is actually a weighted average of the numerators, or a weighted average of this 1, 2, and 3. It's just where all the weights have the exact same weight. And this is always true of the average, because what the average does is it takes the amount of numbers you have, right, so let's say 7 numbers, and divides them by 7. So that means we're basically taking each of those numbers, we're multiplying them by a 1 over 7, and since we have 7 of those 1 over 7s, we end up getting 1, right? Exact same thing with this 1 over 3 situation. So this is a true statement. Every average can be kind of split up in this way and written more clearly as a weighted average. And if you want some more practice with that, that came from episode 45 of the series. All right, part B says the following diagram represents 5/6 times 2/5. So we saw that one way that we could represent multiplication was by doing kind of a diagram like this, where we look at the areas that they resemble. So this resembles 2/5, and it's maybe a little hard to see these lines here, but 2 of these 5 rectangles are shaded in on the side here. And then 5/6, well, we have 5 of these 6 rectangles represented on the side here. And we know that with multiplication, that basically produces an area when you multiply things, right? Like 3 times 4, we could think about that as being 3 tall by 4 wide, and that's essentially the area, or we get 12. That was one perspective we had on multiplication. So we just extended it here where we basically kind of combined their shaded areas and everything else wasn't shaded. So on kind of a first glance, it looks like this should be true, right? We have 2/5 shaded in and we have 5/6 shaded in here. The only thing is there's this gap between this, right? So this gap represents actually a whole number. So this isn't 5/6. These are actually thirds, right? We have a group of 3 here and a group of 3 here. And we have 1, 2, 3, 4, 5 thirds shaded in. So what B actually represents, so the diagram actually represents, so this is 2/5. And then this isn't 5/6, this is 5/3. Reason being is that, again, we have the split after 3 of these parts, and the split represents a whole. So this is actually a whole and 2 out of 3 pieces being multiplied by the 2/5. So we actually get this 2/5 times 5/3, not the 2/5 times 5/6. So part B is going to be false. And part B we discussed in episode 35 of the series. Part C says a 17 out of 25 probability generator can be made in Minecraft. So the way we made probability generators in Minecraft is we essentially took a dispenser, which was like a little face guy, and it will shoot out an item at random from its inventory. And in its inventory, there are 9 available slots. So what that meant is that we could have any probability from out of 2 all the way up to out of 9. So a 1 and 2 probability would be possible by putting 2 items in here, or a something in 9 probability would be possible by putting 9 items in here. But essentially we can make anything ranging from a half to a ninth. And we saw that we could combine these by using AND gates, and AND gates essentially allowed us to do the probability of one and the other, and that multiplies 2 probabilities. So what we want to see now is essentially, can we make 17 over 25 by using that idea? Well, we know that we can make probabilities out of 5. All we have to do is just fill up 5 of the slots of the dropper there. And so to get 25, well, 25, we need 5 times 5, right? So that means if we just do 2 probabilities out of 5, we will get our 25 in the denominator. However, for the numerator, can we get a 17? Well, 17 is a prime number, right? So its only factors are 1 in itself, which means that we would need to somehow get 17 options in the numerator. But since we only have options 2 through 9, it's starting to look like maybe 17 isn't going to be available to us, because we can't fill in 17 slots when there's only 9 of them, right? This isn't really a possible probability that we can express within a single dropper. However, we can use the complement. And so the complement is basically the probability of the opposite event happening. So the complement of 17 and 25, we just do 1 minus 17 and 25, and you'll find that's 8 and 25. So we can find the probability for 8 and 25, and that is just going to be, we could do 4/5 times 2/5. Both of these are possible inside of a dropper. All we have to do is basically take 5 slots, so 1, 2, 3, 4, 5, and have 4 of the slots be the event that we're actually looking for. And then in the other dropper, 5 slots again, but this time only 2 of them be what we're looking for. And then we AND these 2 droppers together using an AND gate, and that multiplies their probabilities. So this will basically give us an 8 in 25 chance of happening. But then to negate this, or to apply the complement, we used a NOT gate, or we basically just reversed the signal using a redstone torch. That's how we applied it in the game. But the point is if we apply a negation to this, one way to write the complement is by kind of putting a bar over top. So if we take the complement of this, this will give us the 17 and 25 probability we are looking for. So it can be done in Minecraft. And so this is a true statement.
Question 8.
Question 8 says, around 60% of my pet squids are bioluminescent. So bioluminescent means they just kind of have like this natural glow to them. An example are fireflies, right? At nighttime, they kind of light up. A lot of squids, they live in really deep, deep areas of the ocean where there's not a lot of light, so they kind of light up as well. So this property is called having bioluminescence. And apparently I have pet squids, and 60% of them are bioluminescent. Do I need any more information to actually figure out what number of my squids are bioluminescent? If so, what information do I need? So just knowing 60% of my squids are bioluminescent doesn't give me enough to know how many squids I actually have, because I could have 3/5 of my squids being bioluminescent. I could have 6/10 being bioluminescent. I could have 60/100ths. I could have 600,000ths, right? All of these different numbers, they represent 60%. If that's the case, then I could be having 5, 10, 100, 1,000 squids, and in all of those situations, I could just have the corresponding numerator of bioluminescent squids. So I don't have enough information to know how many squids I have just based on the 60% alone. What do I need to know how many bioluminescent squid I have? Well, I need to know how many squid I have. Because if I know how many squid I have, I can apply the 60% and actually figure out how many of them are bioluminescent. All right, and we kind of discussed this idea of recovering information from a percentage in episode 39.5 of the series.
Question 9.
Question 9 says, without a calculator or writing any workout, calculate the following. And so each of these, we have a percent of a number, and it wants us to basically do these mentally. And we discussed mental math tricks for percentages in episode 40 of the series, so please go check that out if you're not sure how to do these. So for the first part, 32% of 50. So the way we do this mentally is we think, okay, 32% of 50, that's the same thing as 50% of 32. We can flip the percent and the number we're applying the percent to around. So 50% of 32, that's easier to do because 50% is just half. And what's half of 32? It's 16. So we get 16 for part A. For part B, we have 90% of 28. For this one, the trick that we can apply is 90%, that's the complement of 10%. So if I do 10% of 28, which is just going to be 2.8, right? We're sliding that decimal over by 1. Then all I have to do to get 90% is do 28 minus that 2.8, because we're basically removing 10% off the 28, which is going to give us the remaining 90%. So 28 minus 2.8, that gives us 25.2. And for part C, we have 10% of 5,870. Whenever we're applying a 10%, we just slide the decimal to the left by 1. And especially because we have a 0 here, this is a nice simple calculation where we just get 587 as a result. So all of these we can do in our heads if we're well equipped with the percent mental tricks that we talked about in episode 40.
Question 10.
Question 10 says, a new phone costs $1,300 before taxes, and after taxes it's $1,313. So pretty light taxes because it would usually cost a lot more than that, but hey, I guess it's nice in this situation. So it's asking what was the tax applied. We went from $1,300, and then when we added the taxes, we ended up getting $1,313. So the difference between these is $13. That means our tax is $13, right? And what this question should also ask isn't just what was the tax, because that's easy, but it wants to also know what was the tax percent. So the tax percent, basically what percent of 1,300 is 13? Well, to go from 1,300 to 13, we are basically just chopping off these two zeros, right? And chopping off those two zeros is equivalent to us sliding the decimal back 2 places, or equivalent to us dividing by 100. So 1,300 divided by 100, That gives us the $13 that we're looking for. But dividing by 100, that's the same as applying 1 over 100, which is the same as basically 1%. So we're multiplying 1300 by 1%. What that means then is that the tax percent, or the tax rate on this phone, was 1%. And we discussed this in episode 39 of the series.
Question 11.
All right, we're almost done. Hang in there. So question 11 says, Bowmaths 101 has 3 assignments with the same weight as each other and 2 midterms with the same weight as each other. The assignment total is worth 40% of your grade, and the midterms are worth 60% of your grade. And these are the grades that we got. We want to figure out what our final grade was. Okay, so we have 3 assignments, and we have 2 midterms. And the assignments have the same weight as each other, and the midterms have the same weight as each other. So all that means is that essentially whatever we get for these assignments, we can just take their regular average. And we have that the assignments are worth 40% of our grade. So the assignments here, they do have a weight to them, and the midterms, they also have a weight to them of 60%. What we need to do first is we need to figure out what our average was on the assignments. So our assignments were 10%, 80%, and then 9%. So a couple of them we didn't do so hot on. And for the midterm, we got 50% and 90%. So let's start by figuring out the average of our assignments. So the assignment average, well, that's going to be 10% plus 80% plus 9%. And we're going to add these all up and divide it by 3, because that's how you find the average, right? And we can do the average once again because these are all the same weight as each other. And we actually discussed in an earlier problem that the average is just an example of the weighted average where all the weights are the same. So that's what it is in this case here. So when we add up these percents, we get 10 plus 80 plus 9, so we get 99%. And 99 over 3 is 33%. So our average on the assignments is 33%. For the midterm average, well, what we get is 50% plus 90%, and divide those by 2, right? Because we're taking the average of 2 things. 50 plus 90 is 140. 140 over 2 gives us 70%. So our average on the midterms was 70%. So now to find the final grade, we're just going to take our assignment average, which was 33%, and we are going to apply the weight to it. So the weight is 40%. And for the midterms, we're taking our 70%, and we're applying the weight, which was 60% to it. So because our units are in percent, right, we want a grade that's represented in percent, we're going to keep these percentages as normal, because the 33% and the 70%, that's actually what we scored. But the weights, we're going to convert those into decimals. So 40% is a decimal, that is 0.4. And we're applying that to the 33%. And 60% is a decimal, that is 0.6. And we're applying that to the 70%. So when we apply these items, so 0.4 times 33, you can do that on the side or on a calculator. It's kind of beside the point right now, so I'm just going to do that on a calculator, and I get 13.2 for that. For the weight of the 70%, so the 0.6 times the 70, I get 42. When I add these up, I'm going to get 55.5%. So that means the total grade for the class, when I consider all of the weights of everything, was 55.5%. So you just barely scraped by, you barely passed the course. Maybe you should take it again. But in any case, where we talk about averages and weighted averages in depth is going to be episode 45 of the series.
Question 12.
All right, here it is, question 12, final question. Proud of you for making it this far. Suppose in a school, the probability that a person is an atheist is 50%. So let's write that down. And the probability that a person is not Muslim is going to be 80%. So if the chance they're not Muslim is 80%, what's the chance they're Muslim? Well, it's going to be the complement of this, which is 20%, right? So 20% of the students are Muslim. Okay, so we want to figure out the probability that a person is both an atheist and not Muslim. So what's the chance? Okay, so we're combining probabilities here, and the way you combine probabilities through an and is you multiply the two probabilities. However, there is a caveat with this. These probabilities needed to be independent, which means that basically they cannot both occur at the same time, which means that they can't have any influence on each other. However, are these independent events? Well, the answer is no, because if you're an atheist, well, atheists don't believe in God, right? But Muslims do. So if you're an atheist, you're automatically not a Muslim, which means that these are not independent events. Being an atheist directly means you're guaranteed not to be Muslim. However, being not Muslim doesn't guarantee you're an atheist, right? If you're not Muslim, maybe you're a Christian or a Buddhist or something else, right? So being not a Muslim doesn't guarantee you're not an atheist, but being an atheist guarantees that you're not a Muslim. What this means then is that the probability that you're both an atheist and not a Muslim is going to be 50%. Since this is the probability of being an atheist, and that also guarantees that you're not a Muslim if you're an atheist. So this is going to be our probability right there.
Concluding thoughts.
Okay, that's it. We've done it. 12 questions. Good job. I hope you're feeling more confident with the topics that were covered in Unit 4 of the Fundamentals of Algebra series. We've covered an insane amount of math so far, which is pretty cool. So thank you for being along for the journey. And again, if you were confused by these, please go back and check out the videos that I recommended for each of these questions. And if you still have questions, feel free to leave a question in the comments. And I hope you're looking forward to this upcoming unit, which is on order of operations. Technically, I've done a couple of videos on it already, but I've got some really interesting videos planned, and a lot of the videos are not stuff you would cover in a standard curriculum. So I think that you guys are going to enjoy those. So without further ado, you have a good one, you stay groovy, and I'm going to see you in that next juicy BOMAS video.
BOMAS.